In this video, we will be solving a box and a slope problem using Lagrangian mechanics. This formulation of classical mechanics is very powerful, but it can also be confusing at first. This problem will provide a concrete example that will illustrate its versatility over the classical Newtonian method. Let's begin by defining our problem. As you can see, we have a box and a triangular slope. We will label the triangle's height with the letter h, and we will define an angle theta. With these two parameters, we can control the geometry of the slope and hence see the effect on the box's motion. We will also define the origin of our Cartesian coordinate system on the bottom left of the triangle. You may be used to studying the coordinate system on the slope itself when using Newtonian mechanics, as it makes the vector analysis of the forces a little easier. That choice is perfectly valid, and it will work here as well, but we will set our coordinate system at the corner to illustrate the versatility of the Lagrangian approach. So, our central question is, how will the box move? In particular, what will the x of t and the y of t functions be? If we're able to determine these functions, then we can completely describe the box's motion. To answer these questions, we must turn to the Euler-Lagrange equation. This equation is central to Lagrangian mechanics. Now, at first this equation might seem a little overwhelming. I mean, we've got a mixture of partial derivatives, standard derivatives, a funky L, and q's with dots. We'll break this equation down step by step, beginning with the Lagrangian, which is highlighted in green. Now, the Lagrangian is defined as follows. It's the kinetic energy minus the potential energy. So, if you can identify what the kinetic and potential energies of your system are, you can easily find the Lagrangian by subtracting them from each other. And this is really nice, because kinetic and potential energies are scalar quantities, unlike forces which are vectors, which means that these are significantly easier to manipulate mathematically and to find out in the first place. And we'll see how this ease is extended to the problem-solving part of the problem. And so, we figure out what the Lagrangian is, but now let's figure out what the q's represent, which are now highlighted in yellow. Now, you may be used to thinking about q as representing charge and electromagnetism, but this is not what we mean by q here. Instead, q stands for something known as the generalized coordinate. Let's take a look at some examples to understand what we mean by a generalized coordinate. So, in standard Cartesian coordinates, we typically have the following three coordinates. So, we have qi here, and we have x, y, and z. So, this is what we're typically used to dealing with. The way that we can apply this to our concept of generalized coordinates is by setting the index I to be equal to 1, 2, and 3, such that q1 corresponds to x, q2 corresponds to y, and q3 corresponds to z. Now, these are not the only sets of coordinates that we deal with in physics. We can also deal with spherical coordinates, for example, where you might have r, theta, and phi. And so we can write this in terms of qi as q1 equals r, q2 equals theta, and q3 equals phi. As you can see, the index represents the number of dimensions or the number of coordinates that you're working with. And so if we consider our problem, it's worth asking, how many coordinates do we need to precisely track the box's motion? You might be tempted to say that we need 3, right? We're dealing with Cartesian coordinates, x, y, z. But if you notice that the box is trapped to just following the path along the slope, you'll see that it's only moving along the xy plane. In other words, we only need 2 coordinates, which is pretty convenient. And so in this case, we would have q1 equals x and q2 equals y. Now, what about q dot? I mean, that looks a little bit weird. So q dot is notation for the time derivative of qi. So in mechanics, whenever we put a dot in front of a symbol or on top of a symbol, that means that we're taking a time derivative. And so something that will be very important when we're solving these problems is that we're going to treat q dot and q as different symbols. So when we differentiate with respect to qi and qi dot, that means that we're treating them as completely different symbols. And we'll see what we mean by this in the problem-solving step. Now that we've reviewed the Euler-Lagrange equation, let's begin by solving the problem. I've put the relevant equations in the top right corner. Let's start by figuring out the expression for the Lagrangian. Now, the Lagrangian is equal to the kinetic energy minus the potential energy. The kinetic energy can be written as 1/2 mv squared, as we're used to. Now, we don't know what the speed of the box is, right? However, we can rewrite it in terms of our generalized coordinates. Namely, we'll write the kinetic energy as 1/2 times mass times the square of the magnitude of r dot. This might seem a little bit abstract, but note that the r vector is simply the vector that points from the system's origin, here in the bottom left corner, to the location of the box at any moment in time. So when we put a dot on the r vector, that simply means that we're referring to how fast the box is moving. In other words, the magnitude of r dot represents the velocity, or in this case, the speed of the box. So if we write r dot explicitly, we would have a vector with x dot and y dot, which means that when we take the magnitude of that vector, we're going to get the square root of x dot squared plus y squared, or y dot squared. Plugging this in, we're going to get the expression for the kinetic energy of 1/2 mass times x dot squared plus y dot squared, which we can put here together. Great, so let's put that in the top right corner, and let's now consider the potential energy, which thankfully is significantly more simple. We know that the potential energy, or the gravitational potential energy associated with a gravitational field is mgh, or in this case mgy, as it'll vary as the box moves along the surface of the triangle. And so that's simple enough. It's already expressed in terms of one of our generalized coordinates, and so we can just put that away. We now have k and u, which means that we can figure out what the Lagrangian is. And so plugging that in, we get this expression here. Now, in theory, we could begin by using the Euler-Lagrange equation to figure out the box's equations of motion. Since we have two generalized coordinates, we would need to do this twice, one for x and one for y. However, it's worth asking if we can simplify this problem a little bit more. In particular, we should ask, are x and y independent coordinates? Can we relate them to each other somehow? So, let's see if we can. Let's move the box to some arbitrary position along its path, for example here, with x and y coordinates. Now, notice that we can actually find a hidden triangle here, which I'll highlight here in blue. This triangle is actually mathematically similar to the bigger triangle, the one that represents the slope. This means that, if we pull this out here, we can ask, what is the height of this triangle? Now, notice how the y coordinate of the box is just y, and so the height of this triangle will be h minus y. Now we have a triangle with an angle theta, opposite and adjacent sides. This means that we can use the tangent function to relate them. Solving for y, we get the following expression, which means that we have successfully linked x and y together. Now, as you can see in the kinetic energy equation, we have a y dot there, so we may as well take the time derivative of both sides to get y dot. Differentiating with respect to time, we're going to get y dot equals minus x dot tan theta. Great. Now that we have expressions for y in terms of x, let's substitute them into a Lagrangian. So as we can see, our Lagrangian becomes a little bit uglier, but we can do some simplifications. So firstly, we will factor out the x dot, leaving us with a 1 plus tan squared term. And we can actually simplify this further by using the following identity. 1 plus tan squared equals secant squared. So substituting this in, we get our final form of the Lagrangian. So we can put this up here, and we can now bring in our Euler-Lagrange equation. This is what's going to give us the physics, the equations of motion, which will characterize how the box moves. And so the first thing we have to do is we have to identify how many generalized coordinates we have. In this case, our Lagrangian is just dependent on x and x dot, which means that we can rewrite the Lagrangian in terms of x and x dot. Now, the first step is to compute the left-hand side. So I'm going to put this over here. We have the partial derivative with respect to x of the Lagrangian. Now remember what I said earlier. X and x dot are going to be treated as completely different symbols. If you want to rewrite x dot as like y or z, y might be confusing, but anything else. Now, with this in mind, let's consider what will happen to the first term. It's just a half m x dot squared secant squared theta. Since that is constant with respect to x, it'll completely disappear. It'll get cancelled out. What about the second term, mgh? Well, that's just trivially a constant, and so it'll also be cancelled out. The last term does depend on x. We have mg x tan theta. So that means that when we differentiate, we'll be left with mg tan theta. Great, we figured out half of the puzzle. Let's now figure out the right-hand side. So the right-hand side looks a little bit uglier because we have the time derivative in front, but it's okay. Let's keep in mind what we said before. X dot is a separate symbol from x. With this in mind, let's differentiate with respect to x dot. We have 1/2 m x dot squared secant squared theta. Well, differentiating with respect to x dot, That'll be trivial. We can just pull the 2 down, and we'll get mx dot secant squared theta. The mgh term disappears, and again, x is separate from the x dot, so we'll get 0 for the third term. That means that we'll be left with a time derivative of mx dot secant squared theta. Now, the time derivative might seem a little bit confusing, but the nice thing is that what we can do is we can just differentiate x dot here by just adding an extra dot. So we're effectively differentiating the velocity to get the acceleration here. Double dot means double time derivative. And this is nice. We get unit force here, which is related to the fact that this quantity is referred to as a generalized force. And the partial L partial x dot term is referred to as a generalized momentum. Okay, so we have our two sides here, and we can bring them together now. The physics is now effectively done. We now just have to set both sides equal to each other and solve the resulting differential equation. Notice how both sides share an m factor, which means we can cancel it out. Solving for x double dot, we get g sine theta over cosine theta times 1 over secant squared theta. Of course, 1 over secant squared theta is just equal to cosine squared theta. And so, simplifying the expression, we find that x double dot equals g sine theta cosine theta. Now, this is a relatively simple differential equation. We have a double time derivative on the left and a constant on the right. This means that we can integrate both sides to get our position function. So integrating first, we get x dot equals g sine theta cosine theta t plus v naught. So this tells us about the velocity of the box, where v naught is the initial velocity of the system. Integrating once more, we get 1/2 g sine theta cosine theta t squared plus v naught t plus x naught, where x naught is the initial position. Now, in this problem, we have the box at the very top left of the slope, which means that it has an initial position of 0 and an initial velocity of 0 as well. So, substituting these results in, we get our final expression for x of t, which is 1/2 g sine theta cosine theta t squared. Of course, this one function is not enough to fully determine the motion of the box. We also need a y of t function. And so, we will use the relationship that we found earlier, which is that y equals h minus x tan theta. We now know what x is, so we can simply plug it in. We get y of t equals h minus 1/2 g sine theta cosine theta t squared tan theta, and given that tan theta equals sine theta over cosine theta, we will get that y of t equals h minus 1/2 g sine squared theta times t squared. And here is our final results. These two equations fully characterize the motion of the box. And notice how we did not have to use any forces. We only used the fact that we know the potential energy the system is in, which is gravitational, and the kinetic energy. And even though this problem, you might think that this problem might be easier to solve with forces, this principle, the Lagrangian mechanics approach, can be immensely helpful with more complicated systems. And it can actually provide very deep theoretical insights. For example, understanding the Lagrangian approach and furthermore the Hamiltonian approach will give you insight into how continuous symmetries in the system are related to conserved quantities, and also it'll give you an understanding of the foundations of quantum mechanics. In any case, I hope this approach was helpful in illustrating how this method practically works. I encourage you to approach it using different coordinate systems, and also perhaps not by connecting x and y, but by using two Euler-Lagrange equations to solve for the two equations of motion. You should find that you get the same result. In any case, if this video was helpful, please feel free to leave a like and subscribe, and please let me know if you have any questions in the comments. Thank you very much for watching.